right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. Let's actually just jump into it because we were in the middle of a section last time. So let me share my screen and get everything set up here. Make sure that I can see the chat and all that good stuff. Okay. All right, I think things are good. Hopefully you guys enjoyed the long weekend. Still have a lot of stuff to do. I don't know if you guys are worried about all the stuff you have to do. So we have class today and tomorrow, and then you have a quiz. I think regardless of how far I get tomorrow, I will make the quiz up to sequences. I expect by tomorrow to have started a topic called series, but I will only make the test up to sequences. Maybe I'll throw in some series problems for the bonus. This topic I don't think is going to be that difficult, as long as you remember your limits, which I also sent an email about earlier. So hopefully you guys got that email and maybe you check out some of those resources that I sent before. A big deal with improper integrals. If you're okay with integration, then the issue would be with limits. And so that's going to be the issue here, as well as not even directly dealing with limits, but just the kind of analysis that you would have to do to take a limit. That sort of analysis is very useful in dealing with improper integrals, as well as some topics that we will be seeing in series and sequences. Okay, without further ado, let's just do a quick recap of what we did and continue. So we were talking about improper integrals. So these are basically integrals that, these were definite integrals that didn't quite fit in with the assumptions of the fundamental theorem of calculus. So the fundamental theorem of calculus applied when the function was continuous on the interval AB, and the interval AB was finite so that we could dissect it into n equal pieces of length delta x and all that stuff. And these were finite, the distance between A and B were finite. If either of these conditions are not fulfilled, you end up with a kind of integral called an improper integral. So this is an integral where either the function is discontinuous at a point, one or more points in the interval, or the interval itself is infinite in some sense, in the sense that the lower limit is negative infinity and or the upper limit is positive infinity. A combination of these can happen for a particular limit, so it might not just be exactly one of these things going on. You can have an integral where all of these are issues. The function hits discontinuities and both limits are infinite on the integral. So you can have all sorts of varieties, but any one of those things, the function being discontinuous on the interval AB, perhaps even at the endpoints, the lower limit being negative infinity, the upper limit being positive infinity, any one or several of these things happening will create an improper integral. And we can theoretically calculate these integrals by just using limits. So we set up limits to approach the points of the troubled points. These are points that make the function discontinuous, or the infinite limits. And we pretty much sort of integrate as we usually would. And then we use limits to approach these points. So that was the idea. So in our vernacular, we call these the bad points, the points that made things discontinuous, or if the intervals were infinite. And we pretty much learned that we could compute integrals by integrating as we normally would, but replacing the bad points with just some numbers that we let those numbers inch closer and closer to the problem areas using limits. Ultimately, if we get all the limits converge to a finite number, we say that the integral converges. The geometric interpretation of this is that the area under the curve is going to approach that number. And if you have several integrals, and remember, we have to break up our integrals so that we only have one bad point per integral. If we have several integrals, each of those integrals needs to converge to a finite number for the overall limit to converge. Any one of these limits mess up, it's bad. We learned about a very important kind of integral the integral from 1 to infinity of 1 over x to the p dx, we derive the fact that this converges if and only if p is greater than 1. And then we spoke about the comparison theorems, because it turns out that in general, computing the integral itself in the way that we were doing, like actually to compute the antiderivative and then take the limit of that, that might be very difficult or even impossible to do for certain kinds of functions. So it turns out we have things called the comparison theorems, which allow us to tell whether or not an integral will converge based on knowing about whether or not some other integral converges or not. So this won't actually give you the exact value, but it's a way of using improper integrals, known improper integrals, to determine the convergence of unknown improper integrals. The direct comparison theorem was the first one that we looked at. Basically, this says that if your functions follow the inequality, then if you integrate along that inequality, integrals maintain the inequality. This sort of makes intuitive sense. We saw this in Calc 1. The integral is interpreted as the area under the curve. So if one curve is higher than another curve, the area under this curve is going to be larger than the area under that curve. So taking integrals maintain inequalities. And furthermore, for these kinds of improper integrals, if the upper integral converges to a number, we can conclude that the lower integral converges. And if the lower integral diverges, we can conclude that the upper integral also diverges. Note that they both have to be non-negative, and we have to know what order in which they are increasing. We have to know who is bigger than who. And we have to know that both are greater than 0. Not all the time we'll know this information, though, which leads us to the next comparison theorem, which is the limit comparison theorem. This allows us to do a comparison without actually knowing who's bigger or who's smaller. If we can actually take the ratio and find the limit as x approaches infinity of that ratio, then these two integrals will actually behave the same way. They'll actually either both diverge or both converge. And so if we know about one, we will automatically know about the other. Okay, so that's where we kind of left off last time. Now, in these guys, this theorem is going to be very useful because it's oftentimes we can compare nasty looking integrals to something nice like this one. So that will be a very common thing to come in handy. But I think the best way to actually get used to this is to actually just do some examples. And hopefully you guys actually try these examples on your own already. I did leave the notes on the last lecture, so hopefully you actually took some, tried these things. Now, you will notice for these integrals, they are either impossible to do, or they will actually be very, very difficult to do. I'm pretty sure well, the first one you can probably handle it with partial fractions, because you can factor the denominator by the sum of 2 cubes. Part B, though, is impossible. Like, you can't really integrate cosine squared over 1 plus x squared. This is also impossible. That, I think, is impossible. This, I'm not sure, but I wouldn't want to actually find out. So there are actually issues with directly computing these integrals. And so that's why the comparison theorems will be very useful. So let's actually see how this would go down. Move these guys out the way. Okay, so here is an integral. And let's say I don't want to directly compute it. The example just says, determine whether or not they converge or diverge. So I just want to know, is there a meaningful answer to this integral? Can the area under this curve from 0 to infinity be considered to be finite, right? That's essentially what I'm trying to figure out. And yeah, how would I actually go about doing that without actually doing the integral is the idea. Well, here's one option that I might be able to think. Notice if I take the original and I compare to it something like that, how do these two things compare?
The left one is bigger.
The one on the left is bigger? How do you know?
Because they're basically the same, and then the denominator would just be 1 greater for any value of x.
Yeah, so a bigger denominator in general, if both are positive, a bigger denominator leads to what?
Make it smaller.
Oh, smaller.
It makes it smaller. So the larger denominator is going to make it smaller, right? So, and again, that's actually an intuition that we got from limits. At least it's an intuition that we would explore a lot more when we were covering limits. So the one on the left is actually smaller because it has the larger denominator. Now, both of these are going to be positive. Okay? And the last one is actually just 1 over x squared, which you'll notice actually looks like that 1 over x to the p. It is in fact true to say the following. Okay? Now, what can we say here?
Well, since, can you hear me?
Yes, I can hear you.
Okay, well, since we know 1 over x squared by well, I call it p series, or we know that that one converges, and since the one in the middle is less than it, we know that it also converges.
That is what we'd like to say. There is an issue here, though. Does anyone see the issue with that reasoning?
Is it because the limit's from 0 to infinity and it should be from 1 to infinity?
The limit is from 0 to infinity. In fact, I believe we did this integral before with 0 as the lower limit, and it does not converge. It turns out that this does not converge. Right? In fact, you should look at the theorems very carefully. Notice that in the theorem, the lower limit is actually 1. Whereas here, the lower limit is 0. Having the lower limit 0 is a problem. We actually approach division by 0, and 1 over x squared is not big enough or fast enough to escape the division by 0. So this is an issue. So sometimes you might see a path that you want to apply, but there are issues with that, and it's because it doesn't really match a theorem very well. Now, any ideas for what we can do here to get that to work out better?
Can you use the limit comparison theorem?
Yeah, but compared to what?
Can you compare x over x to the third plus 1 with 1 over x squared?
You could use the comparison theorem here, but I already set it up the inequalities. So let's do the direct comparison. But yeah, you're right. This both can actually work here, but you can also get the direct comparison to work. So let's say you're on a test or a quiz, and the direct comparison theorem is what you actually thought about first. How do you actually get it to work? So instead, here's what we would do. Is that still in red? I would think of I as, so let me call this integral I. What I can do is integrate from 0 to 1. And then integrate from 1 to infinity. Right? Now, the benefits of that is, while I don't know what this is, that's definitely a number. right? No division by 0 is going on. It's not an improper integral. It's just the area under the curve between 0 and 1, and the curve is continuous on that interval. You should be able to see that that is actually just a number. So I can break this integral into two parts, where really it's the second part that's actually giving me trouble. And so what I would think of doing is apply the comparison theorem here. Here's what we can do. So note, 0 is less than or equal to I don't want to throw that integrals in later on. X over x cubed plus 1. Yeah, let me throw in the integrals. Dx, that is equal to 0 to 1 over x cubed plus 1 plus 1 to infinity of x over x cubed plus 1. And that is equal to, let's just call this some number a. So I'm calling this guy here a. And now what I can do is what we were doing before. This is going to be less than or equal to a plus adding this guy instead, because the 1 over x squared, the integral from 1 to infinity is going to be that. And this is known to converge. So let's say that converges to b. I mean, you don't have to go in and write a plus a and b here, but so overall converges. So therefore I can say I converges by the comparison theorem. Now, whenever you're using the direct comparison theorem, you don't have to say direct comparison theorem. Normally, if you just say comparison theorem, it's assumed that you're talking about the direct one. If you're using the limit comparison theorem, you have to emphasize that you're using the limit comparison theorem. But yeah, you can do that. Okay. So be careful about the theorems that you want to use. They are powerful, but they're not all powerful. Everything works in a very specific scenario. Like this is true in math in general, and this is why it's very important that you pay attention to all the rules and the minute details of everything. Being very detail oriented is going to help you a lot. And hopefully that was something that was drilled into you in pre-calc and calc 1, but the need for that gets more and more the higher up you go. So yeah, alternatively, we could use the limit comparison theorem here. Oh, well, we could, but we'd have to do it. You'd still have to break it up. Because you'd actually get in trouble with having the lower limit 0 still. So basically, if I set f of x equals x cubed plus 1 and g of x equals 1 over x squared, this means that L equals the limit of f of x over g of x is going to be equal to, well, x cubed over x cubed plus 1. And limit. And that you would know should converge to 1 based on calculus 1. And so this means the integral from 1 to infinity of x over x cubed plus 1 dx and 1 over x squared dx both converge. And we know they both converge since this converges.
Professor?
Yes.
If you got a positive number like that, but if you knew that 1 over x squared diverged, would they both then diverge?
Diverge, yeah.
Okay.
And you'd have to be aware of the fact that I'm using the lower limit, because one thing in the limit comparison theorem, the only restriction is that you're continuous on the interval, right? So that is an issue, okay? So that's why the limit comparison theorem wouldn't apply if I had the 0 on the denominator, because this function is not continuous at 0. So it's very important that you remember that. Notice the lower limit, because we need to be continuous. Okay. Now, if you don't have continuity, a lot of times what works is the technique that I just showed you. You just break it up into pieces. A part of it will be continuous, or you can deal with that separately. And then the other part, you might use a comparison theorem for, or something of that sort. So yeah, a couple ways you could have dealt with that one, but those are going to be the most common ways. Okay, so here's the next example. Integrating this is impossible with Calc 2 techniques. So we wouldn't try to even integrate that. So what I would do is, again, this is an intuition that we would build up from the Squeeze Theorem. So if you re-watch those lectures that I sent you on Calc 1, in those lectures I talk about the Squeeze Theorem and the idea of building bounds on things that have trig functions, particularly sine, cosine, and the inverse tangent. And so we'd be able to say something like, we know that cosine is between -1 and 1. This, of course, means that cosine squared between 0 and 1. This, of course, means that cosine squared over 1 plus x squared, I just divided by a positive number, 1 plus x squared is greater than or equal to 1, is that. And so, of course, that means, I don't know what's up with that arrow. That means that the integral from 0 to infinity, and we're continuous on when x is 0, going all the way up. So we have this inequality. Now, what can you tell me about this integral?
It's arctangent.
It's arctangent. You can actually compute it, and it would be finite. You could even go better. So you wouldn't even have to compute it. So we can compute this. What would it converge to? Arctangent of x, if you plug in infinity, you get pi over 2. It converges to pi over 2. Or you can even take it a little bit further and just actually compare that one to, say, some constant plus 1 to infinity of 1 over x squared dx, where this constant would represent just the integral from 0 to 1 of 1 over 1 plus x squared, which we would know that actually does converge. Either way, and you know that this would converge as well. Converges by theorem. So ultimately, the integral from 0 to infinity of cosine squared x over 1 plus x squared dx converges by comparison.
I just have a quick question about when you were like creating the bounds.
Mm-hmm.
How did you get or go from the -1 to the 0?
I squared it. If I square something, it's always going to be greater than or equal to 0.
Oh, okay.
So if I have a bunch of numbers between -1 and 1 and I square them, now all their values have to be between 0 and 1. Okay, so let's look at this one. Ideas for this?
Would you also have to use the squeeze theorem for sine squared x?
Sure. What would you what would you say? Well, technically we're not using the squeeze theorem, but the intuition would come from the squeeze theorem. Because if you were to do the squeeze theorem to calculate the limit as x approaches infinity of this thing, that's what you would do, right? We know that our sine squared is between 0 and 1. And so this would mean that 1 is between 1 plus sine squared and 2. And if I can divide both sides by a radical x, all sides by a radical x. 1 plus sine squared x over radical x is less than or equal to 2 over radical x. Radical x is going to be non-negative. It's going to be positive, in fact, when x is 1 or bigger. So I don't have to turn the signs around. So now I have these comparisons. Which one is going to be useful? They're all actually greater than 0. So I would know the following. Okay, give me a conclusion and tell me how you made it.
Well, the first one, the 1 to infinity of 1 over square root of x, we know that diverges because the power of x is a half, which is less than 1.
Right?
And since the second integral, or original one, is larger than one that diverges, it's also going to diverge.
So why didn't you decide to use the 2 over radical x?
Because I'm assuming that one also diverges, but being less than a diverging integral doesn't let us draw any conclusion.
Right. Okay. So notice that we have two things here, but this doesn't help. It does diverge by that same theorem, but being less than a divergent integral means nothing in the comparison theorem, right? So remember when you can make conclusions. If the larger integral converges or if a smaller integral diverges, these are the only two scenarios in which you can make a conclusion from the comparison theorem. So notice that the last integral is useless. However, the first integral that you see there is actually useful because we know it diverges and it's smaller than a divergent integral. So applying the direct comparison theorem here, you would be able to make the conclusion. So we can say that the integral of 1 to infinity of 1 plus sine squared x over radical x dx diverges by comparison with that. So just because you can actually build up an inequality doesn't mean it's actually useful. And sometimes you can build several inequalities, but not all of them are useful. You need to find the one that fits with the theorem that you're talking about. That comes with knowing the theorem very well, and then making sure that what you're looking at to apply the theorem is actually fitting with what the theorem says should happen. What about this? Did anyone get this one? What can you tell me about secant squared? Bounded wise.
It's undefined when x is pi over 2.
Tell me when it's undefined in general. It is undefined at pi over 2, but where else?
Oh, n times pi over 2, where n is any integer.
No. Clean it up a little bit. You're getting warmer though. Anyone wants to help him out? It's n times pi over 2, where n is any odd integer, only for the odds.
Oh,
So your cosine hits 0 at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, etc. plus or minus all of those, right? So n has to be odd. So that is something that you should know. Remember that from Calc 1. So yeah, now, okay, great. We know that it's undefined. How does it behave though? Like, can you tell me some bounds? Like, are there any boundaries that we can put on a secant? So let's start by looking at the cosine.
I guess, so from 0 to 1, it doesn't matter since it won't reach pi over 2.
So this is y equals cosine x. Yeah, but I still, we want to look at the behavior here. And of course, this, it hits 0 here, 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 here. And is that pi over 2? Is that 3 pi over 2? Is that 5 pi over 2? Is that minus pi over 2? Minus 3 pi over 2? Minus 5 pi over 2? Okay, so if I were to draw y equals secant, how would the secant behave? Let's look pointwise. What happens to secant when the cosine hits its maximum? What is the value?
It's 1.
It's 1. So whenever the cosine hits 1, the secant will also hit 1. What about when the cosine hits -1? Secant is also going to hit -1, right? What happens afterwards? Like if let's say I'm at this point here on the y-axis. If I move a little bit to the right, what's going to happen?
It's
To
going
the
to go
graph of
up.
secant. It's going to go up, right? Up where? Like, well, to infinity, right? It's going to go like that. How do I know? I'm dividing by the cosine, and the value of the cosine is going to 0. It's approaching 0 from the right. So I have a fraction where the numerator is positive, and the denominator is approaching 0 from the right. It's going to go up to positive infinity. Similarly, if I move to the left, that's going to happen. A similar argument can show you that all of that is going to happen here. And applying the argument upside down shows you that all of these guys are going to happen here, because then I'm approaching a fraction where the denominator is approaching 0 from the left. So knowing that secant behaves like that, now you didn't have to memorize the graph of secant, but you can kind of actually figure out what the graph would actually look like. Knowing that in blue, what can you tell me about secant in terms of boundaries?
From 0 to 1, it's greater than 1 over x root x.
Or let me be a little bit more to the point here, because in the question, it's not secant. So I have secant squared. What can you tell me about secant squared?
It'll still be greater than 1 over x root x from 0 to 1.
You're talking about the entire integrand, just secant squared alone. Tell me about secant squared, the possible outputs.
Negative infinity to negative, well, negative infinity. Sorry, 1 to infinity.
1 to infinity. It's always going to
Yes.
be bigger than 1, in other words. So, of course, 1 is bigger than 0, but my secant squared is always going to be bigger than that. This, of course, means that's going to be true. Because it's 1 over x, da, da, da. And so what can we actually say?
1 over x root x diverges.
This diverges, right? Right? You think of it as 1 over x to the p, but you're having like a 0 integral on this thing here. Okay, so a lot of this comes down to knowing how to build bounds and all that stuff, because inequalities are going to be important for you to be able to build. In this case, limit comparison theorem actually wouldn't really work out, because if you take, for example, this function and divide by that function, you would get secant squared as the result. And that limit does not converge, right? So the limit as x approaches infinity of secant squared does not converge. So the limit comparison theorem would actually be, you can't apply the limit comparison theorem here.
What are other instances in which you can't apply that?
Okay, so that is a great question. And we are now at the point where I can give you the talk about life and how to say, a lot of times when you are in a lower math class, a question like that would only have a few cases that I could talk about and I could explore every possible scenario with you. It's no longer true. So there aren't really a list of specific cases that I can come up with and I can tell you, okay, in this scenario, you always know that. It's very hard to describe it. What I would say is you should use the theorem itself as a guide. You basically want to know that what you're looking at has to fit this theorem. Now, in regards to this theorem, you notice that what you need is you need to be able to compute this limit, which means the situation that you're in is going to depend on, can I compute this limit and determine an answer? And unless you can actually do that, then you can't get this to work. So pretty much in any scenario, if you want some general guidelines, in any scenario where you actually can't compute the limit of the ratios, like if you want to compare the function you're given to some other function, but you cannot compute the limit of the ratio, then you can't use this. As well as if you're not continuous on the interval, you can't use this, right? If you want to get some broad guidelines. As to specific instances that I can point out to you where these things always happen, there's an infinite variety of possibilities there. But you just have to make sure that what you're looking at, you can actually apply. You're in the situation where the base assumptions of the theorem would apply. And the limit actually won't work out in this situation. So I know that a lot of students would have the idea that, you know what, building inequalities is complicated and I need to figure out who's bigger than who in order to apply the direct comparison theorem test. So you know what, I'm just gonna forget about it and always apply the limit comparison theorem test. Well, I see where you're going and I like the fact that you want to be more efficient, but it just turns out that you can't always be efficient because each of these theorems have a very specific set of assumptions and scenarios under which they can work. And sometimes one can work while the other one won't work. Sometimes both can work and one is easier. And yeah, I can't really tell you delineate every possible case because it really varies on the problem that you're looking at. So you just have to get used to being able to read the theorem, know what criteria needs to be satisfied in order for you to apply the theorem, see if you can apply that criteria, and that's how you know what can work from what cannot work. In general, also as a rough guideline, I would say always try to apply the direct comparison theorem first. And then if you realize that nothing is coming to mind or you just can't get it to work, maybe consider the limit comparison theorem. But this is an example of when the limit comparison theorem would not work, while the direct comparison theorem would. And that's because of the presence of the trig function makes it very difficult to actually, the limit, because the trig functions has asymptotes and all sorts of stuff. So the limit is not going to work out very well. Whew. Okay, last question. Where are we? Okay, what do we want to do here? So if you wanted to do direct comparison theorem or any comparison theorem, what do you think we want to compare it to?
If you like use the powers here, it's like 3/5. So then you could say that that's like 2 in the denominator. So like technically you'd want to use something a little bigger than like 1/x².
1/x². Okay, so
Okay.
that suggestion actually highlights a very important intuition. Again, an important intuition that you would get from limits. And if you go back and watch the lectures I sent you guys on limits, you'll see where all that is coming from. In Calc 1, we learned that as you're going off to infinity, the higher the degree of the polynomial, the more powerful it is, to the point where all the other polynomials just kind of don't matter. They kind of fall out. So if we look at all of these power functions individually, x cubed, x to the 5th, 2x, 1, and 10, when we're going off to the infinity, in the numerator, the x and the 10, completely irrelevant. You can actually pretty much ignore them because the x cubed is going to be the dominating power in the numerator. If you look at the denominator, the dominating power is going to be the x to the 5th because our x is going off to infinity. And so essentially what you would do is when you want to figure out what you want to compare things to and you have something like this, the goal is to figure out who are the dominating elements. And you also remember something else you learned in limits is that when it comes to dominating elements as you're going off to infinity, logs are less than polynomials. This is a general rough thing, less than exponentials, less than factorials, less than, maybe I should write examples of these. So you can see like the symbols I would talk. If you're in general, let's say you're looking at log to the base a of n, that is considered to be smaller than n to the a, which is considered to be smaller than a to the n, which is considered to be smaller than n factorial, which is considered to be smaller than n to the n as n goes to infinity and a is bigger than 1, right? So these are some intuition that you build from Calc 1. So I went over this in the Calc 1 lecture, so I'm not going to go over that anymore. But even within these categories, within each category, there is also the idea that n to the a is going to be much less than n to the b if your b is bigger than a, right? And within this category, your a to the n is going to be much less than b to the n if your b is bigger than a, etc. So within each category, there's a hierarchy of who the top dog is. And across the different kinds of functions, there's a hierarchy of who the top dog is. So you are going to consider that. So that's the intuition that we're using here. Whenever you want to figure out what you want to compare something to, this intuition is invaluable. So when you look at something, you know you want to use a comparison theorem because I don't want to integrate that. You focus on the highest powers or the top dog. if there were, for example, an e to the x in the denominator, I would actually ignore the x to the fifth in favor of that e to the x, because I know that polynomials are less powerful than exponentials, etc., for example. So I would only focus on the larger powers. So that leads me to, I want to compare this guy, the x cubed plus x plus 10, over the x to the fifth plus 2x plus 1. The most efficient comparison, that's pretty much straightforward, is just comparing it to the x cubed over x to the fifth, right? So essentially all of these guys I can actually just ignore because I'm going off to infinity. And my concepts that I have from limits tells me that I can just ignore the other guys. So now I pose that question to you. How do these compare? And this guy, of course, is going to be 1 over x squared. So if I look at 1 over x squared, and I were to ask you, is it this or is it that? Right? So if I were to ask you how these compare, what would you say? Who's bigger?
I'm not sure which one's
Aren't they the
bigger.
same?
Why not? Why aren't you sure?
Yeah, I was gonna say because they're the same, and then I was gonna say also like couldn't you just use like 1 over x cubed?
They're not the same. The limits are the same, but these guys are not the same. For example, I can plug in x equals 0 on the left side. I cannot plug it in on the right side. If I plug in x equals 1 on the left side, I would get a different answer than if I were to plug in x equals 1 on the right side. So they're not the same. As far as limits are concerned, they would approach the same thing, but I'm not talking about a limit. I'm actually talking about an integral, which is a little bit more complicated, right? So strictly speaking, they're not the same. So who would be bigger in general? So it turns out in this case, not obvious who. I mean, you could go make an argument for why you might think one is bigger than the other, but it's going to be a lot more work than you'd want to have to handle. How do I know it's not, how do I know it's not obvious? That's the first thing. Like, why can't I just actually rush in and guess here? So why is it obvious? Because notice that this guy here, or maybe, why is it not obvious? Because to go from and again, this is using intuitions from limits. So tell me about the denominator, smaller or bigger? So if I want to, I need to make so if I had the original to go to the one on the right, did I have to make the denominator smaller or bigger?
Smaller.
The denominator on the right is smaller, right? And when you have a smaller denominator, what do you get?
Bigger number.
Right. Need to make the denominator smaller. So we should get a larger fraction. Case closed? Not quite. But at the same time, if I look at the numerator, what kind of change would have to happen in the numerator? I would need to make the numerator is also smaller, you would notice, right? Because I went from taking the x cubed plus something, and I reduced it. I ignored the plus somethings. So now the numerator is also smaller. So we should get a smaller fraction. So here's why it's not obvious. In order to make the comparison that I want to make, I would have to make changes that are competing against each other, right? So one change is to make the denominator smaller, but simultaneously I'm making the numerator smaller. One change is making a bigger quantity, while the other change is making a smaller quantity. I'm both making things bigger and smaller simultaneously. How do I know who is going to win? How do I know if the bigger that I made it is bigger than the smaller that I've made it? You know what I mean? Like you'd have to go into some sort of argument to say, oh, I know that this change would overwhelm that change. And that takes a lot of calculation, right? So like, which wins? Like, not obvious, right? Would reducing the numerator by x plus 10 be more of a bigger change than reducing the denominator by 2x plus 1? I mean, they're both linear functions. As x is going off to infinity, they're roughly the same. Like I don't know who's going to be a bigger change as I go off to infinity, right? It's just not obvious. Okay, so when you first encounter an integral like this, the first thing you're going to want to know to do is what is the best thing to actually compare it to? Intuition from limits is going to help you. I wrote down some of the intuition, but beyond that, you can go watch the old lectures that I linked you to. But then there's also once you know who you want to compare it to, how do you actually know how they compare to each other? There might be issues with that. Before, it was pretty obvious. In the earlier example, like it was pretty obvious. X over x cubed plus 1 compared to 1 over x squared. Obviously, the one on the right is bigger because the only change occurred in the denominator. I made the denominator smaller. So I know for a fact that this is bigger. It's not ambiguous. It's not, there's nothing to actually worry about. In this scenario though, when I compared it to the obvious thing, notice that I actually affected two changes where I'm not sure how it actually works out. So I'm not sure who's bigger or smaller. So suggestions, what can we do here?
Limit comparison.
Limit comparison, right? So this is an example in which the direct comparison would be an issue to apply, but the limit comparison isn't. So the important thing for the direct comparison theorem is that I need to know which way the inequalities are pointing, right? I need to know who is bigger than who in order to make the conclusion, right? If I have issues in determining that, I can't use a direct comparison. For the limit comparison, I need to have the limit existing to be able to make a conclusion. If I can't get the limit to exist and the thing isn't continuous on the interval, I can't use the limit comparison, right? So this is a situation in which the direct comparison has issues, but the limit comparison doesn't. See, for the limit comparison, the answer is actually pretty obvious. If I call this guy f of x and call that guy g of x, so here, direct comparison is an issue. So here is where you would think. So think maybe a limit comparison. And then you can see, would a limit comparison work? On Are both of these functions continuous on the interval from 1 to infinity? Yeah, because I'm not dividing by 0. So the continuity requirement is fulfilled. What about the limit requirement? So f and g are continuous on 1 to infinity. And if I take L equals the limit as x approaches infinity of f of x over g of x, this is going to be the limit as x approaches infinity of, well, it's going to be x squared times the original, which is x, I believe was x cubed plus 10x plus 1 over x to the 5th plus 2x plus 1. I forgot what
The numerator
x
is
plus
x
10.
plus 10.
X plus 10, and the denominator is 2x plus 1. Okay, what is that answer?
X to the 5th.
1.
It's 1, right? Which is greater than 0. So limit comparison applies. Limit comparison theorem applies. And I can actually know. So yeah, this integral, the integral that I would compare it to, is actually 1 to infinity of this guy. And we know that converges by theorem. So this means that this integral converges by limit comparison.
Professor,
Yes,
why couldn't, when you were doing the direct comparison theorem, why couldn't you just use like 1 over x cubed?
because it's not a good comparison to make. Because the biggest powers on the original are x cubed over x to the 5th. This fraction, as I go off to infinity, behaves like x cubed over x to the 5th, which means it behaves like a 1 over x squared. It does not behave like a 1 over x cubed.
But like, didn't we talk about how like, if it's 1 over x to the p, then we know that it's convergent?
Yeah? No. You have to be a little bit more specific. If we go from 1 to infinity, yes.
Right, so then why can't you use any value for p for this one?
You can, but the best thing to compare it to would be this. Right, you don't want to compare it to some outlandish function. Like, you're not making random comparisons here. Right, you do want to compare it to something that you'd be able to control, or you'd kind of know what's going on. Like, I wouldn't think of 1 over x cubed as behaving similarly to this given function. 1 over x squared would behave similarly.
But then I was just saying, because then you would know if it's greater or smaller, so you could do the comparison.
You would know for sure that 1 over x cubed is greater?
Well, I mean, no, that would be smaller, but I'm saying, like, you would know that for certain.
Is that certain? So there are a couple things for that. If the smaller one, it converges, it doesn't mean anything. So I wouldn't be able to conclude anything. But how are you so certain that 1 over x cubed is going to be smaller?
I mean, I'm not, but you could use, I mean, I guess you could just use like 1 over x to the 10th or something. Like something that you know would be smaller.
Yeah, but how would you know? Like, that's what I'm saying. Like, you're just throwing out a guess where, I mean, you'd have to come up with an argument for why you know that's smaller. And again, if you come up with something that's smaller, it doesn't help with direct comparison, right? A smaller integral converges tells you nothing about the original integral. right? Direct comparison, you need something larger to converge, or you need something smaller to diverge. So if you throw out there, okay, 1 over x to the 10th, and you claim that that is smaller than the original, yeah, the integral from 1 to infinity of 1 over x to the 10th does converge, but it's smaller. So, okay, it means nothing. Like, it doesn't tell me anything.
Okay.
Right? For the comparison theorem, if I find a smaller thing that converges, it's meaningless. It's useless. So again, it comes down to knowing what the theorems say. And in box here, no conclusion can be made in any other cases, right? So if the bigger one converges, I can conclude that the smaller one converges. Or if the smaller one diverges, I conclude that the bigger one diverges. Every other scenario, I can't make any conclusions. So even if you could construct something where it's obvious that it would, I don't see an obvious construction here to get something bigger that converges. That's obviously bigger. Right, here there are just too many elements. You have to make too many changes to get to a reasonable comparison, right? And again, I wouldn't go throwing out something random. Like if I have a 3rd degree polynomial over a 5th degree polynomial, I mean, comparing it to like 1 over a 10th degree polynomial is just kind of out there. Like why would you do that? It's very out there. The best thing to compare it to would be to something that looks like the higher powers. So yeah, I think that was the last example. So comparing to something that's too far away can run you into a lot of issues. And again, this is something that we've seen in limits in Calc 1. The comparison, what you're comparing it to actually makes a difference. You have to have a good choice to compare things to. Okay. That's all I want to say about that. I think want to maybe talk about the setup for the next topic, maybe. Maybe I can even get through some examples here. Okay, so we saw about how to integrate integrals of various functions, and we now see that sometimes if we have like improper integrals, we can deal with those, both in cases where we can actually compute the antiderivative and when we can't directly compute the antiderivative. However, you'll notice that with the comparison theorem, when we cannot actually directly compute the antiderivative, it doesn't actually give us an answer. It just kind of tells us that an answer is out there, that the answer exists, right? However, for a lot of situations, we actually do want an answer. So sometimes, like knowing, for example, going back to the previous scenario. So for example, I know that this guy converges, but what if I wanted to get an answer? Like, what does it converge to? Is it close to 5? Is it close to 17? Is it close to 1,000,000? Like, what would the answer be? Give me a ballpark. And I need to know actually with some reasonable degree of specificity what this would actually converge to, right? So the comparison theorem can tell you that something converges, but it doesn't tell you converge to what exactly. The comparison theorem tells you that the answer is out there, but what is the answer? We don't know. This leads us to an idea called numerical integration. This is when our fancy pants, sophisticated, high-minded strategies can't really get us to a specific enough answer. So we actually go about doing things based on first principles. So this is when we come down to, let's just go back to the actual definition of what it means for an integral to exist and to compute one and to actually just approximate it. You actually did this in Calc 1 again. This was when you learned about the right-hand rule, the left-hand rule, and the midpoint rule, and you were constructing Riemann sums, and you basically can approximate a definite integral by using the sum of the areas of rectangles, right? So that, you actually use that to actually build up to the fundamental theorem of calculus. That was all derived in Calc 1, so I'm not going to do that again. So we are going to go back to those principles here. right? So every now and then you'll have an integral where, yeah, all your fancy pants strategies can't actually get you to an answer, but it's very, very important that you be able to get to an answer. And so what you try to do is something called numerical integration. And this is basically kind of like going back to first principles of integration, setting up Riemann sums. So in Calc 1, you learned about 3 of these strategies. There was something called the left-hand rule. So this is like if you have, let's say, a function doing its thing, and you care about the area from A to B. And what you did was, okay, you went in and you dissected this into a bunch of subintervals is what you called it. And left-hand rule basically said that the left side of each subinterval, you extend it up, and that would touch the function. The left side touches the function. The left side of this subinterval touches the function. The left side of the subinterval touches the function. And then you can kind of actually approximate the area under the curve by adding up these rectangles. And you actually did that. The length of each of these, the length between here was what we call delta x. And you might recall that in general, delta x was equal to b minus a over n, where n is the number of subintervals. Which was also, it's equivalent to the number of rectangles. Okay, so this was how you can actually approximate the area under a curve using rectangles, where the left-hand endpoint actually tells you how to construct these rectangles. And the heights of all these rectangles are given by the function itself. So the height of this one would be, of course, given by f of a. The height of this one, so this is like x1, x2, x3. So the height of this one would be given by f of x3 and x so on. And we can actually add these guys all up. We also learned about the midpoint rule. So let's say take a very similar kind of function. I care about finding the area under the curve between A and B. So again, what we could do is we could actually cut this up into several subintervals. But in this time, what we did was we chose the midpoint of those intervals to determine the height of the function. Someone got kicked out. Let me let them back in. To determine the height of the function. And so our rectangles would look like this. And again, we add up the areas of all these rectangles, take all the f of x values, multiply by the delta x values, add them all up, and that would give you an approximation for the area under the curve. We also looked at and this is all back in Calc 1, so that's why I'm really rushing over this, because I do expect you to know about this already. So for the right hand, it's a similar treatment. We dissected this into a number of subintervals. And in this case, we let the right side determine the height. So I connected the right side of all the intervals to the function. And that right side is what determined the height. And we learned a lot of important concepts, like, for example, when our function is decreasing, it should be obvious from these pictures that I drew that the left hand is going to give you an overestimate for the area, because the area of the rectangles will always be larger. The right hand would give you an obvious underestimate for the area. And the midpoint was kind of meant to be a middle ground between these two, because on one side I get the overestimate, while on the other side I get an underestimate, and this kind of balances out easier. The reverse of all that is true if the function was increasing. But if the function is moving up and down, then it's kind of not obvious how these estimates would actually work. out. But in some cases, it was pretty much obvious. So we had those guys from Calc 1. So now, essentially what we're going to be doing, so overestimate versus underestimate. So in the above example, if I did the left-hand rule versus the midpoint rule versus the right-hand rule, this one gave you an overestimate. This one gave you an underestimate. And this one, well, you don't know, but it's more accurate than the other two. In this particular case, the midpoint isn't always most accurate. So these are just, it based on a case-by-case basis, right? But that sort of analysis you would have done in Calc 1. Okay, so here's what we're going to do, is sometimes we want to get even better approximation than rectangles. And so we might wonder, well, why would you use rectangles all the time? Like a rectangle always has a flat top, but this curve is actually moving down or up and down. Like, isn't there something better to use than rectangles? And that's what we're going to talk about. So these three were the methods that we learned in Calc 1, but I actually want to introduce two other methods to you. And tomorrow we're actually going to look at how to apply these methods. So the idea is using trapezoids was another idea. Let's look at this same example here. Let's say this is A to B. And again, I do all these sub-intervals. So, but here's the thing. Instead of using the left or the right side, I'm going to use both sides of the interval. So connect all of these guys. And what I'm going to do instead is connect these with a straight line. You'll notice that this creates a bunch of trapezoids, right? Like rectangles with a slanted roof, right? And this you will see in this particular example, these guys seem to hug the curve a lot nicer than any of the previous three methods did. And of course, knowing the area of a trapezoid, we'd actually be able to figure out what is the area of each of these guys. So for example, if the base is delta x, call this x0, call this x1, call that x2, call that x3, call that x4, or whatever. We know that the area here is going to be 1/2 the sum of the lengths of the two parallel sides times the distance between them. The area here is 1/2 times the sum of the lengths of the two parallel sides times the distance between them, and so on, etc. Now what you'd realize, if you kind of add these guys up together, you would end up with something like delta x over 2 times f of x0 plus f of x1 plus delta x over 2 times f of x1 plus f of x2 plus, let's actually just extend this example. It's going to keep going until I end up with the last one, f of xn minus 1 plus f of xn. In which case you'd realize that x over 2 is a common term. And on top of that, these guys here are the same, which the inner ones, you'll notice that all the inner ones repeat. And so this can be thought of as delta x over 2 times, well, f of x0 plus 2 times f of x1 plus 2 times f of x2 plus dot, dot, dot. And it goes all the way up to 2 times f of xn plus f of 2 times f of xn minus 1 plus f of xn. This leads to something that we call the trapezoid rule, right? So it turns out there are other ways, there are many other ways, but we're going to actually cover 2 of them. The trapezoid rule is another way to actually do this kind of analysis on an integral, except instead of using rectangles, we use trapezoids. And this is the formula for it. And I kind of explained to you where that formula came from. And of course, I just want to remind you that your delta x is going to be b minus a over n. Now, of course, if your if we have infinite limits, then of course you just replace that with a number. Do this this list here, and then take the limit of the answer, and you can do that. We're not going to do anything like that, though. We'll only apply these strategies that I'm telling you to finite intervals. But this is another idea. There's also the idea of using parabolas, which will be nicer, which are nice in some cases. This leads to Simpson's rule, which I'll derive that for you tomorrow, which is, it's not big enough, leads to this guy, and I'll talk about that a little bit tomorrow as well. But I just wanted to introduce to you the idea that we can use other ways to actually approximate areas under curves. So I'll leave these guys in the notes, and I'll talk about where this rule comes from tomorrow. And then we're going to actually apply them to solving an example. So basically, I'm going to show you how to kind of use 2 new strategies for approximating areas under curves, which again, can come in handy when we want to actually find an answer that we might not be able to otherwise find an answer. What I would say is definitely look up limits for tomorrow's class. Review your limits from Calc 1 if you haven't already, and just go back over your notes, review the left-hand rule, the right-hand rule, the midpoint rule. Conceptually, these guys are still going to be important. However, the focus is going to be on the trapezoid rule and Simpson's rule. Let me make that focus, trapezoid rule. And Simpson's rule. As in Simpson's 1/3 rule. There are other versions of Simpson's rule, but we're only going to do the 1/3 rule, right? So again, now if your curve is like wavy, you might realize, why am I using a shape that has straight lines at all? Why should I use a rectangle or a trapezoid? Maybe I should use something that curves. And then when you start to think, okay, let's use a bunch of parabolas, right? That's what leads to Simpson's rule. And I'm going to derive that for you tomorrow. But these are just some new ideas I want you guys thinking about for tomorrow, because I would go through the examples here. We're not going to focus on estimates, really, just knowing how to compute these directly, which is going to be very similar to computing left-hand, right-hand, and midpoint rules from Calc 1. Super similar, just that you're using a different formula. I'm going to talk about where the formulas come from and how to apply them tomorrow. As well as tomorrow, I will start sequences. So we'll kind of wrap up there. I will post all these notes, and I will give you, I will see you guys tomorrow.
Thank you.
Okay, you're welcome.
Where will you?
Come again?
Where will you post the notes?
Same way, in the video description of the lectures, like always.
Okay.
I'll post a PDF of today's notes. All right, I think that is it. Thank you for your attention. Have a good night. Have fun studying, and I guess I will see you guys in the next one. Ciao.